curve. So on these curves, you see the free flow speed, okay, and every curve starts from the free flow speed of the road, and up to a point, the free flow speed remains, okay, or the speed is equal to free flow speed, and after that point, you see that the speed starts to reduce. So the point up to which the speed is equal to free flow speed, we call that as a break point, PP. Okay, so if your flow rate is under this point, then your speed equals to free flow speed. And if you are in this region, the curve region, then the speed is calculated using this big scary equation. So this equation is to be used when flow rate is more than break point. Okay, so here we need the free flow speed itself. Either you measure it or calculate it. We need the speed adjustment factor. SAF stands for speed adjustment factor. We need C, which is the capacity of the highway, from these equations, one of these equations. Then we need the flow rate, which comes from here. Okay, what else do we need? We need the capacity adjustment factor as well. CF stands for capacity adjustment factor. Now, whether we should take free flow speed equal to free flow speed, whether we should take speed equal to free flow speed, or should we calculate it using this equation, depends upon the comparison of flow rate and break point. So you need to calculate the break point as well. So this is how we calculate the break point. Okay, again you need the free flow speed, the speed adjustment factor, and the capacity adjustment factor. Three things here. So once you have the flow rate and the break point, you can decide should the speed equal to free flow speed or should the speed equal to this whole thing. Okay, but one of these conditions will eventually give you the speed. Once you have the speed, then you can calculate density as flow rate upon speed. Okay, so density is flow rate upon speed. So flow rate already calculated and speed one of these. You have density, and density is linked with the level of service. Okay, so you will put the density over here and you will see which level of service you have. Okay, so for some of the highways, the capacity is already given, and what is the speed at capacity is also given. The speed at capacity means speed at this point, the end of the curve. Okay, this is capacity. For every curve, the end point is the capacity. Okay, and what they are giving here, average speed at capacity, is the y-axis at this point, the end point. Okay, so when the curve ends, the x-axis shows the capacity and the y-axis has a average speed, and these values are given here. Now if you look at these curves, they already have the level of service. Okay, so last time I believe I showed you that if you know the speed and the flow rate, you can insert them into this curves and you can see which level of service you have. For example, if your flow rate is 1000, so that means you are here, and your so you go from here and then you have to search which one is your free flow speed. So let's say my free flow speed is 60. So I go from 1000 up, my free flow speed is 60, so on this curve. Okay, so you can see this curve is in level of service B. So I can say my level of service is B. I don't need the density and I don't need the speed as well. Okay, so this can be done. You can use these curves. to find out the level of service directly, and you can come to this table and find out the capacity and the average speed at capacity as well, only if your free flow speed matches these values. Okay, if your free flow speed doesn't match, then these curves cannot be used. Okay, these curves cannot be used. You have to go back to density, and then you have to calculate the speed, then density, and then go back to the table to find out the level of service. Okay, so this is a very simple question here because the free flow speed is 70 and I have 70 here. Okay, so it's a 4-lane freeway, urban area and whatever. The peak hour volume in one direction is given. Okay, so whenever we are doing the analysis for these uninterrupted flow facilities, we are always doing it for one direction. Okay, so we have 6% trucks with 30-70 mix, 30 is single unit trucks and 70 is trailer trucks. The gradient is 2.5% over a length of 1.25 miles. Peak hour factor is given. Okay, whenever we start with these questions, first thing you should look at is the free flow speed given, and the answer is yes, the free flow speed is given. Then you move on to the second step, which is the flow rate. So I go back to the equation for flow rate. This is the equation for flow rate. Number of lanes are given in the question. Peak hour factor is given, but FHV, factor for heavy vehicles, is not given. So I need to calculate it. And this is the equation for factor of heavy vehicles. Here I need percentage of trucks and I need the equivalency factor for trucks. If I look at the question, percentage of trucks is 6% and the equivalency factor depends upon terrain, the gradient. The gradient is given here. Either the gradient is given or the terrain conditions are given. Okay, so I'm here. Okay, and I have a mix of 30-70. Why this mix is important? Because I have tables for the adjustment factor. These are the tables for adjustment factor. Okay, so you can see the distribution of single unit trucks and trailer trucks is mentioned here. Okay, I have 30-70, 30 single unit and 70 trailer trucks, which is this one. Okay, so I go here, my gradient is 2.5% and my length is 1.25 miles and I have 6% trucks. So 6% is this one. So 2.5, 1.25 miles and 6% trucks. So my factor is 3.36. My equivalency factor is 3.36. Percentage of trucks 6%. So factor for heavy vehicles 1 divided by 1 plus percentage of trucks into 3.36, the equivalency factor minus 1. How much is this? Yes, how much is the heavy vehicle factor? Okay. So after that, I can calculate the flow rate. Okay, so peak hour factor, as I said, is given. Number of lanes. Now, if it's a four lane freeway, four lane is two directions, but I told you the volume is one direction. So you need lanes in one direction, four lane for both. So that means two for each direction. And peak hour factor is 0.92. So the flow rate will be volume, peak hour factor, number of lanes, and the factor for heavy vehicles. How much is that? Okay, so once we have the, and which one is correct? Yeah. Okay, so once we have this, so our flow rate is 1359. Now since we have the free flow speed and the free flow speed appears here, okay, that means I can use the curve. Okay, so 1359 is somewhere here, okay, in the middle, and then I go up to the curve of 70. So you can see my level of service is C. Okay, so in this case the level of service is C. Just for the sake of explanation, let's say I don't want to use a curve. Okay, let's say if I don't want to use a curve, then what will be the procedure? The next step is you find out the breakpoint. Okay, we will not do it, but the next thing you should do is find out the breakpoint. Okay, now in this equation you can see adjustment factors are here, but there is no condition mentioned which requires adjustment in the question. Okay, so we will just ignore these factors. Okay, we will just use free flow speed for the breakpoint. Okay, once you have the breakpoint, then you will check if your flow rate is more than the breakpoint or less than the breakpoint. Okay, if the flow rate was less than the breakpoint, so let's say the breakpoint is 2000, your flow rate is less than the breakpoint, that means your speed equals to free flow speed. So you will do flow rate upon speed, which will be free flow speed, find out density, and then use this table to find out the level of service, this one. Okay, and if your breakpoint was less and the flow rate is more, so let's say your breakpoint is 1000, but your breakpoint is 1000 and the flow rate is 1300 something, so that means your flow rate is more than the breakpoint, and you will use this big equation. Again, you will ignore the adjustment factors, just use the equation without them, and you find out the speed, and you will do flow rate upon speed, you will get density, and you go back to the same table to find out the level of service. So these are this is if you cannot use the graph, and as I said, the graph should only be used if the free flow speed matches the ones which are given in the graph. So if my free flow speed had been 72, then I would have done the calculations myself. Okay, another thing is you can see in the graph you can see these lines. Okay, so how did, or what are these lines representing? They are representing a level of service. Basically the inclined lines are representing level of service, and you can see the density of each level of service, maximum density of each level of service is written on these lines. Okay, so what does density has to do with the graph? Okay, how can I plot the lines using the density on this graph? The graph is between flow rate and speed. Okay, and density equals to what? Flow rate upon speed. Okay, so density is basically the slope of this line in the graph. Okay, slope measured from the x-axis, remember. oh sorry, yeah, slope measured from the y-axis. Okay, because speed is here, right? Speed should be the speed is denominator, right? Base. Okay, so uh, these density values are basically slope measured from the y-axis. Okay, because flow rate upon speed is the slope. Okay, now in all these equations, I said if the conditions are not given, you will ignore the adjustment factors. But what conditions will require us to calculate the or put the adjustment factor? Okay, so there are certain conditions. If you have them in the question or in the field, you need the adjustment factors. So the first condition is related to the weather. Okay, so some of the weather conditions, they may require you to have the adjustment factors, the speed and the capacity. So you can see the conditions in this graph, the weather conditions and the two factors, the speed adjustment factor as well as the capacity adjustment factor. Okay, so if a weather condition is given, for example heavy snow, so you will go there and you will find out what is the speed adjustment factor, what is the capacity adjustment factor, and you will use them in these equations. Okay, SAF and CAF. Then another condition could be for the incident. The highway is facing an incident and that incident is resulting in a lane closure. So one of the lanes is closed or maybe more than one lane is closed. So this table gives you uh, the capacity adjustment factor for lane closure. Okay, so we only have the capacity adjustment factor for the lane closure. We don't have speed adjustment factor for lane closure. Okay, so lane closure only has CF. Okay, not SAF. So these values are CF. Okay, so if lane closure is given because of an incident, you will get the factor from here. Now you can see here, if I have two lanes, so the factor for two lane closure is not applicable, three lane closure not applicable, four lane closure not applicable. Okay, why is that? Because if I have two lanes and both of them are closed, that means the highway is closed. So there is no point doing the analysis over here. Okay, so that's why you see not applicable means either the highway is closed or the value is not possible. So two lanes, three lane closure is not possible, four lane closure is not possible. Okay, so the values which are written as not applicable here are actually not applicable. Okay, then we have the adjustment factor for driver population. Okay, driver population means how many drivers are familiar with the road. Okay, so these are the adjustment factors for them. Again, we have both of them now, capacity adjustment factor as well as speed adjustment factor. Okay, so let's say in the previous example, the one which we had here, this one, we have the weather has medium rain. Okay, so what will be the effect on level of service for that? Okay, so if I go here, the medium rain is this one, the first one, and it has speed adjustment factor as well as capacity adjustment factor, both. Okay, now the first two steps remain the same, free flow speed and the flow rate. Okay, free flow speed and the flow rate, both of them are not affected by these values here. Now the point is, can I use these graphs? In this case, if adjustment factor is to be applied, can I use these graphs? And the answer is no. If an adjustment factor is to be applied, these graphs cannot be used. They are without adjustments. Okay, so I cannot just simply plug in the value and look for an answer. So I have to do the entire procedure. Okay, so first thing is after the flow rate, I have to find out the breakpoint. Okay, so I'll go back. What are the adjustment factors here? For speed, 0.96. and the capacity is 0.9276. Okay, so my breakpoint, you can see this big equation over here. So 1000 plus 40 into 75 minus free flow speed into speed adjustment factor 0.96. Okay, and this whole thing multiply by capacity adjustment factor square. So how much is that? Yes, how much is the breakpoint? Okay, so the next step is, now remember all these values, the breakpoint and the flow rate, are in passenger cars per hour per lane. Okay, so the next thing we need to do is compare the flow rate with the breakpoint. The flow rate is higher. It was, remember, 1300 something. Okay, so I have to use this big equation. Now I cannot write this equation in the chat, so you need to do the calculations yourself. Okay, you already have the values. Okay, free flow speed is 70. Capacity, we need to find out capacity. Yes, so there is one more step we need to do, which is to find out capacity. We are dealing with freeway here, so capacity will come from this one. Okay, so 2200 10 70 minus 50. How much is capacity here? Very simple equation, 2200 plus 10 into 20, 200 plus basically. So 2400 I believe, right? And again, this is also in passenger cars per hour per lane. Okay, so this is my capacity. So you have all the values now. You can use this equation to give me the free flow speed. So we use this equation. Now remember this is a condition, okay? The condition because of which we are using the equation. This is not part of the equation. So equation ends at this square, at this bracket square, okay? So what is the speed here now? Tell me. Yes. What is the free flow speed here? Yes, the speed. How much is it? No, your speed is 70, free flow speed is 70 and speed is 9 only. It's not possible. Yes, somebody else, or then you can check your value. Oh my god. So you're using this equation, right? So we have 70 into 0.96 minus 70 into 0.96 minus capacity is 2400 0.9276 divided by 45, this whole thing divided by capacity 9276 minus the breakpoint 1268 square equals this one. Okay, and this whole ratio multiplied by EP, which is 1359 minus 1268 square. This is what we are trying to do. So how much will you get? Yeah, this makes more sense. Okay, so moving on. Now we can calculate the density. Density is the flow rate upon speed. Okay, so yes. So my flow rate is 135 59. Okay, and I can put the speed as exact as I want. So how much is my density? Okay, so now I will go to the table to find out what is my level of service. Okay, so you see 20 is over here, so my level of service is C. Anyone has any questions? Everything is fine? Okay. Okay, there's another set of adjustment factors, CF and SAF for the work zone. Okay, which needs to be calculated. Up till now, I have shown you adjustment factors in the form of tables, but this one needs some calculations. So we are trying to calculate CAF and SAF for the work zone. What do we mean by work zone? Work zone means some construction work going on either on the highway or on the side of the highway. Okay, work zone means construction maintenance work going on the highway or on the side of the highway. So first thing you need to calculate and the calculation is pretty much same for CAF and SAF both. For example, the first thing you are going to calculate is QDR, Q discharge rate. So the calculation of Q discharge rate is required for CAF as well as SAF, both of them. So you can see in this equation, the QDR equation, we have some factors. The first factor is called as factor for lane closure severity index, FLCSI. Factor for lane closure severity index. How do we get it? We have to calculate from this ratio. Okay, now you can see OR and N naught. OR stands for open ratio, which is number of open lanes divided by original number of lanes. So you may have some lanes closed because of the construction activity. So those are called as open lanes. So open lanes divided by what lanes we had before the work zone in normal conditions. You divide them and you get OR, and N naught is number of open lanes. So open lanes itself is N naught. Okay, so this equation will give you FLCSI. Then you have factor for barrier type. If you are, so barrier type means what? If this is my work zone, by law you have to put some barrier between the work zone and the lanes of the road. Okay, so this is the barrier we are talking about, and it is applicable in most of the cases because we don't want the cars or the vehicles to go into the work zone. So we put a barrier there, and if that barrier is made up of concrete, then FBR becomes 0. Otherwise FBR is 1 for any other barrier. Non-concrete barrier, FBR is 1. Next factor is for area type. If the area is urban, factor is 0. The area is rural, the factor is 1. The next factor or the next distance is the lateral clearance. Lateral clearance between the barrier, remember there is a barrier. So from the barrier till the lane, the distance is called as the FLAT. Okay, the lateral clearance distance. So from the barrier to the lane, FLAT, and then we have the factor for day and night. So if you are performing the analysis for daytime, the factor is 0. If performing the analysis for nighttime, there is a factor of 1. Okay, so this will give you Q discharge rate. You need to calculate one value and the rest of the values will be from here, 0 or 1. Then after you have the Q discharge rate, you can calculate the CAF for work zone. Q discharge rate divided by 0.864 multiplied by capacity. So the capacity we used or the capacity we calculated in the previous question is the base capacity. Okay, so base capacity is the simple one which you have calculated in the last question. Okay, so this is for CAF. Then for SAF, you will use this equation first, which will give you the free flow speed in the work zone. You need the speed ratio factor. Speed ratio means work zone speed upon non-work zone speed. Speed limit, we are talking about speed limit basically. So work zone, so when we have work zone, sometimes the government may decide to reduce the speed limit of the road because we have some dangerous or risky element on the road. So that speed limit divided by the original without work zone speed limit. So their ratio is FSR. Then the second factor is speed limit in the work zone, the one which you are using in this ratio. Okay, so that is speed itself. Okay, so the ratio goes here and the speed itself goes here. FLCSI, same as this one. FBR, factor for barrier type. This one. Factor for day and night. This one, 0 or 1. Then we have factor for number of ramps. Okay, this is so just number of ramps. You have to count the number of ramps here. Okay, so how many ramps you have on your segment basically. Okay, and you get free flow speed of the work zone. Then you take the ratio of free flow speed of the work zone from normal free flow speed, and you will get SAF for the work zone. Okay, so this is how you do it. So we have an example, and the example, if you look at the first line, it says it's a long-term work zone. So I want to explain something important here. So we have looked at the adjustment factor for weather conditions, for example, in the last example, and this one is for work zone. Now let's say if you are dealing with Bahrain. Okay, so we know the weather conditions in 80% or maybe even 90% of the year is same. We have shiny sunny weather 90% of the year. Okay, so should I take a work zone, or sorry, should I take a factor for adjustment for weather in these conditions? Then the answer should be no. Okay, the weather condition adjustment factor should be taken in countries where this medium rain persists for a very long time. So most of the year you have this rainy weather, like in the tropical region or something. Okay, same applies to work zone as well. If I have a work zone which has like a duration of 1 day, so should I take or should I calculate the work zone factors because of 1 day, or should I focus on the rest of the 365 days? Okay, so the answer is I should focus on the rest of the days, not the 1 day of the work zone. So work zone is like a anomaly. It's something rare, something exceptional. Okay, so we look for normal conditions. If the normal conditions have that weather, have that work zone, or then we will consider it. So for example, if we are building a bridge, we have a metro project or something, so the work zone because of these projects normally take months and years. Okay, so that will be a long-term work zone, and then it will make sense to consider the adjustment factor for it. Okay, so this is what they have specifically mentioned in the first line of this example. The freeway has 8 lanes, 2 in each direction, 2 of which are closed due to a zone. Okay, and 2 out of 8 are closed. Okay, 2 out of 8 are closed. So free flow speed is given before the work zone. They are using concrete barriers. They have zero clearance from the barrier to the lane. It's in rural area. The critical operation is during the day. Critical means the peak hour. Okay, critical is what is critical for speed? The peak hour. The peak hour is in the day. Speed limit through the work zone is 45. Without the work zone, it was 70. Okay, and the total ramp density on the freeway is 3 ramps per mile. Okay, they already mentioned it. I did not explain it here. So let me explain. Ramp density means what? You count number of ramps you have, divide by the length. This is called as ramp density. So you can see here number of ramps per mile here. So this is what they are using here. Okay, we are using ramps per mile here. So number of ramps divided by the length, ramps per mile. Okay, so that is 3. So we are not using number here, although they are saying use number of ramps, but this is ramp density. So they need number of ramps per mile basically. Okay, for these conditions we have to find out the capacity and free flow speed of the work zone, and after doing that we will find out the adjustment factors as well. Okay, so we start from here, the Q discharge rate. The first factor I need to find out is the lane closure severity index, FSCSI, 1 divided by number of open lanes. Remember, I had 8 lanes. Out of 8, 2 are closed, but these 8 are in 2 lanes, 2 directions. Okay, so out of 8 from 2 directions, 2 are closed. That means from each direction 1 is closed. From each direction 1 is closed. Okay, so 8 means each direction has 4 lanes. Out of 4, 1 is closed. I have 3 open lanes now. Okay, and the openness ratio, which is number of open lanes divided by the normal lanes. So how much is that? Okay, so now I can calculate my Q discharge rate. So 2093 minus 154, 0.44 minus 194. Factor for barrier type, my barrier is concrete, so this becomes 0. Then factor for area type, my area is rural, so 1. Then factor for lateral distance, my lateral distance is 0. Okay, so this becomes 0 as well. Plus 0. And then factor for day and night, we are doing the operations during, or we are considering the operations during daytime, so this also becomes 0. Okay, so what is my Q discharge rate here? Okay, so this is my Q discharge rate. I need the base capacity as well. For the base capacity, we have this equation. Still we are dealing with freeway. Okay, my free flow speed is 70, right? Yeah, it's 70. Okay, so I already did it last time as well. Same value. Okay, so this is my capacity. Now I go and calculate the Q discharge, sorry, the capacity adjustment factor for the work zone. Okay, so how much is that? 1846.864. How much is that? Okay, 0.89. Now if you want the capacity of the work zone, it's not written here, but I will tell you. If I want capacity in the work zone, then I will take the normal capacity multiply by the CF of the work zone. Okay, which they are asking in the question, right? So normal capacity is 2400, the one which I got from here, and multiply by the adjustment factor. So this will give you capacity of the work zone. How much is that? Okay, so capacity of the work zone is done. Then we need the free flow speed of the work zone, which is coming from here. Okay, so I need the speed ratio, work zone speed upon non-work zone speed. Work zone speed is 45, the normal one is 70. How much is that? Okay, so now I can use this equation now. Free flow speed of the work zone minus 5.6 CSI, which we already calculated, 0.44. The barrier type was 0, so this, concrete, so this becomes 0. Factor for day and night, we are doing during daytime, so this also becomes 0. And then we have the ramps density, which is 3 here. So minus 1.45 into 3. Okay, so how much is this factor? This is what now? Free flow speed of the work zone. Sorry for that. So this will give you free flow speed of the work zone directly, not the adjustment factor. This is for the free flow speed of the work zone. So how much is that? Okay, so now if you need the, so you got free flow speed of the work zone directly. Okay, but if you are going to use them in the level of service equations, then you need the adjustment factor of the work zone, right? So if you have this, then this is your free flow speed of the work zone, and this is your normal free flow speed. So this ratio will give you the speed adjustment factor. Okay, so the value you calculated earlier is the free flow speed itself of the work zone, not the adjustment factor. This will give you the adjustment factor. So in the case of capacity, you will calculate the adjustment factor and you multiply the normal capacity with the adjustment factor to get the capacity of the work zone. For the speed, you can directly get the speed of the work zone, free flow speed of the work zone, using the equation. Okay, so there's a slight difference between how these two are calculated. Okay, any questions, any problems? Okay, we have another example which is for level of service design. It's a design example. So we have a new freeway, and it is to be designed in a level terrain. The heavy vehicle factor is given, peak hour factor is given. Okay, the free flow speed is given. The freeway needs to accommodate 4,000 vehicles per hour during the peak hour in one direction. Okay, so one direction volume is given, and how many lanes you will go for if you need level of service C, and how many lanes you will go for if you need level of service D. So we need to check for two conditions over here. Okay, so as I mentioned previously in these questions, the first thing you look for is free flow speed. If it is not given, you will calculate it. Fortunately, it is given here, and there are no adjustment conditions given here. No work zone, weather, driver familiarity, or incidents. So we don't have to worry about the adjustment factor here. We can use the graphs directly then. If you remember, I showed you the graphs. So one of the free flow speed on the graphs is 65. We can use it. But what we need to know is the flow rate. Okay, we need to know the flow rate. So the flow rate is, we have used it earlier, volume, okay, divide by number of lanes, peak hour factor, which is 0.88, and factor for heavy vehicles, which is 0.93. Okay, so now in this question you can see that we have two unknowns in this equation. There's another way to find out, but we are not covering it in this course. Okay, we already covered that other method in traffic engineering. So people who didn't take traffic engineering, they will take, and we will cover this method with them over there. But here we will use another method, which is using the graphs directly. Okay, so we have two unknowns, n and vp. Okay, so if I can put vp over here, then I can find out the value of n. Okay, so how do I get vp over here? I'll go to my graphs. Okay, 65. Okay, my free flow speed is 65. I'm looking for level of service C, so this one, and level of service D, so this one. Okay, so what we do is we go over here, level of service C is here. Okay, I go to the x-axis and find out the value at level of service C, and I do the same thing for level of service D as well, which is over here. Okay, so I go there and find out. So for example, if let's say from here level of service C is intersecting is, let's say, 1700. Okay, so my VP will become 1700. Okay, and if I go for level of service D, then I'm here. So let's say which is 2100. So this is at level of service C, and this is at level of service D. Okay, so how many lanes we will get in each case for C and D? How many lanes? Yes, how many number of lanes you got? You're using this equation. Okay, so in both cases, almost 3 lanes. Okay, you cannot give 2.3 and 2.8. You will go for 3 lanes. Okay, so it doesn't matter. You will eventually end up giving 3 lanes. Okay, so I hope this is clear. Okay, now I'll move on to the calculations of other parts of the freeway. Now, the calculations which we have done up till now, they apply to freeways, okay, and they apply to multi-lane highways, okay, but they apply to specific sections of them. For freeway, they apply to sections which are away from the ramp by at least 1500 feet. Okay, they apply to sections of the freeway which are at least 1500 feet from the 1500 feet away from the ramp. So if you are this much close to the ramp, then the calculation which we have done will not apply there. Okay, and if you try to apply the same thing to multi-lane highway, then they are done in the sections which are not near the intersections. Sections which are not near the intersections. Okay, there's no limit given for that. I haven't seen any limit for that, but you can like have an idea. If you are too close to the intersection, then that methodology will not apply there. Okay, because multi-lane highways can have intersections and freeways have ramps. So according to them, you have to see. So if you are away from the intersection and away from the ramp, you know what methodology we have to apply to find out level of service and design. Now, if you are close to the ramp, why ramps are different? Because near the ramps, lane changing happens more often, because people will either try to go on the ramp or they may be coming from the ramp onto the freeway. Okay, so this will create more turbulence, more lane changing on the freeway itself. So that's why this particular part cannot be considered same as the rest of the freeway. Rest of the freeway, they don't have ramps, so the lane changing is normal, it's less. Okay, but near the ramps it happens very often. And we have two types of ramps. You have entry ramp and exit ramp. So you can see both of them over here. Okay, so if you have an entry ramp, then it will cause lane changing in the area after the ramp. If you have an exit ramp, then it will cause lane changing in the area before the ramp. Okay, so the area which is under this heavy lane changing is called the influence area. Okay, ramp influence area. Okay, so for entry it is after the entry, for exit it is before the exit. Okay, so we call them ramp influence area. And how much is this area? This is the first 2 lanes of the freeway. First 2 lanes mean the lanes which are near the ramp, up to a distance of 1500 feet, 1500 feet. Okay, so the ramp influence area is 2 first lanes to a distance of 1500 feet. Okay, and which 1500 feet depends upon whether you have an entry ramp or an exit ramp. For entry ramp it will be after, for exit ramp it is before. You see another terminology written here which is the gore point. Okay, so gore point is basically the connection point between the ramp and the freeway. This point over here and this point over here. Okay, so the extreme connection point between the ramp and the freeway is called the gore point. So gore point is what we use to measure the 1500 feet of influence area. Okay, so and the first 2 lanes are the flow in the first 2 lanes is termed as B12. Okay, so you can see the methodology is written here, how to calculate the level of service for these areas. Now if you have an entry ramp, people are trying to merge on the freeway, so we call it the merge area or merge segment, and this segment is 1500 feet. If you have an exit ramp, then people are going to diverge from the freeway to the ramp, so we call it the diverge segment, and again it is 1500 feet before the ramp. Okay, so this one is after, this one is before. Okay, so this is the methodology. First of all, find out the input data, then you calculate how much flow you have in the ramp influence area, the first two lanes. You have to calculate the capacity of these areas, then you will calculate the density and find out the level of service, and then in the end you can find out the speed and aggregate density for these areas. What do we mean by that? We will come to it. Okay, let us first of all look at the, so now we were calculating the flow rate earlier as well for the simple freeway and multi-lane example. Here you have the flow rate as well. We are using peak hour factor. So we take the volume, divide by peak hour factor and divide by factor of heavy vehicle. There's something which is missing here from the last equation which we were using. What is that thing? What is missing here in the flow rate equation? There's one factor missing in the denominator. Which factor is that? We're using that factor in the previous examples. So which factor is that? Which factor we were dividing for simple freeway and multi-lane, but we are not doing it here. Yes, can anyone tell me what factor we are missing here? No, in the flow rate, this is the flow rate equation. Vp is flow rate. Okay, so when we are calculating Vp, we were doing V upon peak hour factor into FHV into something. What is that something? This is what I'm asking. Yeah, number of lanes. Okay, so we are not using number of lanes. That means this is the total flow, not flow per lane. Okay, why we are doing this? Because then later on we are interested in finding out the flow for the first two lanes. Okay, so this is the next step. So the first step is you should know the free flow speed. This remains the first step. The second step is to find out the flow rate total, which is VF. So total volume divided by peak hour factor and factor of heavy vehicles. The total volume of the freeway, not the ramp, freeway. Then you will find out the flow for the first two lanes. If your highway has only two lanes, in one direction, then this step is not required. Okay, so this step will only be required when you have more than two lanes, because if you have only two lanes, then your flow is in two lanes. Okay, if you have only two lanes in one direction, then your flow is, your VF is in two lanes. Okay, so you don't go to this step. Okay, but if you have three lanes in one direction or four lanes in one direction, then you have to do this step. Okay, so again you have to look whether you have a merge section or diverge section. If you have a merge section, then this is what you do. If you have a diverge section, this is what you will do. So VF is coming from here in both the equations. VR is the flow rate on the ramp, and this is only required for diverge section. So out of the freeway, how much will go on the ramp? Okay, because freeway already has a ramp volume. Now people will exit. Okay, so how much will be that exit? So this will be the VR. Okay, so now you can see that we have proportion factor for merge section and proportion factor for diverge section for these. So how do we get this? Yeah, so I will only explain these conditions today, and later on we can see yeah, we have some examples as well. So next time we start with the examples. Let me explain the conditions over here. Okay, PFM, which is for merge section equation. Now remember, you don't need to apply both these equations in one question, because either you have a merge section or you will have a diverge section. You cannot have both. Okay, one section can be merge or diverge, not both. Okay, so let's say if you have a merge section, then you look at these tables and these conditions. Okay, if you have 4 lanes, that means 2 lanes in each direction. Your PFM is 1. You don't need any calculation. You are done. If you have 6 lanes, means 3 lanes in each direction. Or if you have 8 lanes, means 4 lanes in each direction. Then you have to look into one of these conditions. Okay. So if you have 3 lanes in each direction, you can do it from here, here, or here. You can see equation numbers are given here. So if I have 6 lanes, 3 in each direction, then I have 3 options to calculate PFM. If I have 4 lanes in each direction, then I have 2 options to calculate the PFM. Which option should I go for? This table will tell you. So you need this table to select the equation for the last 2 conditions. Okay, and this table tells you, or this table requires you to know the ramp situation. Okay, on all of them are on ramps, right? Because you have a merge section. Merge section has on ramp, entry ramp. Okay, what is your upstream ramp? Meaning the ramp before. So you have a ramp in your section, and you have to look at the ramp before, upstream, and the ramp after, which is downstream. So your ramp is on, no upstream, no downstream. You should use equation 5.28. No upstream, and the downstream is also on, meaning merge, meaning entry. Then you should again use equation 5.28. No ramp upstream, and the downstream one is off, meaning diverge, exit. Then you can use 5.28 or 5.30. Okay, which one? This will depend upon D and LEQ. Okay, what is D? D is the distance between these 2 ramps. Distance between these 2 ramps. Okay, the subject ramp and the off ramp. Okay, so the distance between the 2 ramps which you are comparing. Okay, which you are putting here. So that will be D. What is LEQ? LEQ will come from these equations. Okay, so if you are calculating LEQ for upstream off ramp, you will use this equation. If you are calculating LEQ for downstream off ramp, you will just use this equation. What is VD? The flow on the downstream ramp. VD is flow on the downstream ramp. And what is LA? The length of the acceleration lane. What is acceleration lane? When you will come on the ramp, you will have a small lane here, so that you can regain your speed before you merge on the main highway. This is called as acceleration lane. And since we are already discussing it, on the diverge section we'll have a deceleration lane. So when you are going off the highway, you will come to this small lane and you can reduce your speed before you go on the exit. So this is called as deceleration lane. Okay, so merge section has acceleration lane, the diverge section has deceleration lane. Okay, so these are 2 lanes we are talking about. So the length of this lane is acceleration lane. Okay, so from here to the end of the lane. So this will be my LA. Okay, so LA is this one. VF is the freeway flow rate, and VR is the ramp flow rate. Okay, SFR is the free flow speed on the ramp. Free flow speed on the ramp. Okay, so first of all, you will see you have 4 lanes, 6 lanes, or 8 lanes. If you have 4 lanes, no problem. If you have 6 lanes or 8 lanes, you have multiple options. Which options to go for? You have to look into this table. And this table, there are some conditions which require you to compare between D and LEQ. Okay, so D is the distance between the two ramps, and LEQ will come from one of these equations. Okay, so downstream of ramp, down upstream of ramp. Okay, so you will take this into this table, know your option, go here, find out PFM. Okay, and then you will go here and put PFM here to get V12, the flow rate in the first 2 lanes. For diverge, we have similar conditions. We have PFD now, again 4 lane, PFD is 1, 6 lanes, you have 3 options. 8 lanes, you have only one value here. So 8 lanes, again your life is very simple. You don't have any options. So diverge in this case is simpler. Diverge means exit ramp. Okay, but if you have 6 lanes, that means you have to select between one of these 3. Again, you will come to this table, you look at your conditions, and you will look at what options you should go for. Like we had LEQ in the previous case, we have LEQ here as well, but LEQ equations are different now. Okay, we have another value here which is L up. Okay, so L up is the distance between the ramp and the upstream ramp, your ramp and the upstream ramp, sorry, this one. Okay, so upstream ramp, this one. Okay, so D is to the downstream ramp, basically. D is general. D can be D is for the downstream, I believe. No, D can be for the upstream as well. Yeah. Okay, so D is general. Okay, we will do some examples to make it clear, but D is something general. D can be to the upstream or the downstream depending upon which LEQ you are comparing with, and L up means it is to the upstream always. Okay, so D is general and this one is like this. Okay, so we don't have the time to do the examples. Do you have any questions?